First, a very brief introduction into. Oh, does it not work? 1 second. Demo effects. There we go. So, who am I? My name is Steven Warmelink. I have a background in artificial intelligence. Got my bachelor's and my master's degree here right in Groningen. I've been working at the Hanze University of Applied Sciences since 2019. Initially as a researcher, and slowly I started picking up teaching as well. But we're here specifically for one of the projects that I've been working on for the previous 2 years, which is the so-called Wattflex project, in which we researched to what extent we can use batteries to balance the electricity grid. And it's both for, let's say, the smaller consumers who may have solar panels and a small home battery, but we also explore to what extent you can use an industrial-sized battery next to a solar park. So the entire story in one slide is the grid needs to be balanced at all times, and can we actually use batteries there? Are they the solution? Who knows? Who can tell me what this is? This image, what it represents? Yeah, you wanna? Yeah, the average global temperature, I think it's since 1870-ish. They're called warming stripes, very similar to warning stripes for a reason. Global warming is an issue. We're shifting towards renewables, but one of the main issues with shifting from, let's say, coal to wind power or solar is the volatility, right? If you turn on a coal plant or a gas central, you always know what output you're going to get, and it's going to be constant, so it's easy to manage the grid. But as we are getting more and more renewables, like solar, like wind, for example, here it's projected that by 2030, compared to 2017, the amount of electricity generated by non-renewables will be halved, while the proportion generated by renewables, like solar and wind, will quintuple, so 5 times as much. So it's going to be a way larger percentage of our power that's generated by these renewables. But they're really volatile, right? So one day might look like this. The yellow curve is solar power production, and the blue ones are off and onshore wind turbines. But another day might not be as windy, and it might look like this. Or it might be a really non-sunny day. And as the grid operator, you need to make sure that consumption and production of energy are balanced at all times. If there's ever a time where they're not in balance, you can get rolling blackouts, and that's well, a very big issue. So how does this grid operator, TenneT in our case, does this? You basically have 2 different energy markets that you can trade on in order to balance the grid. You have a day ahead, which is a longer term market. If you have a dynamic contract with prices per hour, that's also the prices you as a consumer use. You also have a short-term market called the AFRR market. Usually for consumers, that's off limits because you need a lot of, let's say, power to be able to trade on that market, at least 1 megawatt. But for industrial-sized companies or parties, that's a possibility. So we're going to see to what extent are batteries a solution to, well, basically move energy from one place in time to another to reduce these swings in production and consumption. For that, we're looking at 2 scenarios, a small scenario and a big scenario. The one is home batteries, and the other one is industrial batteries near solar parks. So first, the more, let's say, engaging example, which is home batteries. Who of you own solar parks? PV panels. Okay, about almost 2/3 of the room, I would say. And how many of you have a home battery? 1. Okay. It's for sale. Spoilers. All right. So we're going to look at 3 different cases for home batteries, basically almost like business cases. The first one is arbitrage, by which I mean basically just buying low and selling high on this dynamic 1 hour pricing market. The other one is self-usage, so try to use as much energy that you produce yourself with your solar panels by storing it in your battery instead of discharging it to the grid and then using it later on when you have not enough power. And the last one is fixing imbalance, by which we mean you cannot do that on your own. You need to be part of a bigger group of people who do that at the same time to reduce the imbalance on the electricity grid on a shorter time scale. So in case of arbitrage, you can only do it if you have a dynamic contract. So only if you have the 1 hour pricing contract, so not the daltarief and hoogtarief in Dutch. And during summer, it usually means you charge on your solar power and later on discharge it for whatever the market price is at that point. Self-usage speaks for itself. You just put the battery that you would otherwise discharge to the grid in your battery and later on use it if you have a shortage. And the imbalance, you need an aggregator to do that because you need at least 1 megawatt, which is a lot because most, let's say, residential batteries are around 5 to 20 kilowatts. So we need at least 50 of the large ones to be able to meet the demand. And for imbalance, at this point in time, you can actually earn back your battery relatively quickly, but the future of to what extent that's going to stay that way is relatively unclear because the salderingsregeling or net metering arrangement is going to disappear in a couple of years, and that has a big impact there. All right, so the small scenario, home batteries, and in this case, arbitrage. So selling low and buying low and selling high, obviously, not the other way around. In our project, we had a bunch of households that were part of the project and had a home battery installed as part of the project. And of course, you can do all kinds of fancy machine learning to try to figure out when should I charge, when should I not. But it turns out that in this case, you can also just use linear programming because there's one optimal solution if you don't account for self-optimization. So in this case, the question is, do I charge once? Do I charge twice? Or maybe do I not charge at all? Is the spread between buying low and selling high big enough given my efficiency and the purchasing cost of my battery? So for those of you who are familiar with linear programming, you may be able to parse this, but it comes down to basically a constraint satisfaction, right? So you need to make sure that your battery state of charge remains within certain bounds. You need to make sure that if you go for one of these charging cycles, that it's profitable enough given the price of your battery, etc. And this is what comes out. As mentioned, as part of this experiment, we had data of real-world households. This is historical data, so we have about 250 households that all have PV panels. And what we did was first we did basically a retrospective analysis of what would have happened if you installed a virtual battery at those households. So let's take a random day, the 18th of July in 2021. So right here, what you would expect is if you install a battery, because right now this graph on the left, this graph on the left signifies what happens if you don't have a battery. So around 7 a.m., you start discharging to the grid because you produce more than you consume. And then towards the evening, you start taking energy from the grid instead. So if you would install a battery and not do anything with self-optimization, right? It's just charging when prices are low and discharging when prices are high. So then you would look at what is the cheapest moment in time where I can start charging my battery. You charge your battery, and what's the most expensive hour or hours where I can discharge my battery and discharge there. So this is basically the outcome of the linear programming experiment. In this case, only this spread is big enough to warrant charging and discharging. Sometimes there are days where 2 of those peaks are big enough that you can charge twice in a day. Concretely, what does this mean? We analyzed 3 different years because we have a lot of data. And it turns out that over the course of a year, depending on how much production or consumption you have, you can earn, let's say, from 150 to 400 euros. Well, what does it mean? It only means something if you know how expensive a battery is, right? These batteries are roughly 6,000 euros a piece. Can you do the math on the ROI, return on investment? How long does it take? 5 years? It's almost more like 15 years. So these, just doing arbitrage on a home battery at this point in time is not profitable. That's the bottom line. All right, so we also did it live in practice. This is what it looked like, because charging your battery with this type of battery is slower than discharging, so you need 2 hours to charge. But if everybody would, for example, have a home battery and start doing this at the same time, you have the issue of net congestion. You read about it almost every other week in the news. This was about 2 months ago. Like home batteries can increase electricity net issues. Also, some of the net or grid operators, they put infographics online saying, okay, please, if you want to use your home battery, please use it for self-consumption instead of trading on all these different energy markets, because you're screwing up the balance on the grid. And why is that? Because if everybody on this graph in your town has a home battery and they all start charging their batteries at the same time, you get issues with your, what's it called in English? Transformator? Transformer, thank you. So that's something you want to avoid, and maybe it is a nice bridge to, I don't know who of you were at the talk in Camera 1 this morning, the first one on context matters. Well, here context matters as well. If you optimize for yourself, you might get the most money out of it, but for the system as a whole, it's a big issue, right? All right, so self-usage is another really interesting one, right? Because at least from an idealistic perspective, it sounds really nice to be able to use more of the energy that you generate yourself by storing it in a battery, and then later on in the evening using it. So what happens if you have, let's say, a naive control mechanism? So here on the left is an energy profile of a household during the day. So first you start using energy, you start using more, then the sun starts shining and you start returning energy to the grid. Now, if you compare that to the energy prices for that same day, there's basically an alignment problem, right? Because if you start placing a battery here and you would start charging here, the issue would be that you still start charging when you don't have the lowest price yet. And you start discharging when you're not at the highest price yet. If you start discharging later, you save more money, right? Because the electricity prices are higher there. So don't do that. Instead, try to do that. Well, what does it take to be able to do that? You need to be able to predict the electricity prices. Well, we don't need to predict them because they're readily available the day in advance, because these are the day ahead prices. But in order to effectively do this, you also need to be able to predict your own production and consumption. And that is a harder part, because that is really dependent on the household that you have and the type of house, how many PV panels, etc. So what makes it difficult specifically? So predicting production, you can do it using weather data. In the case of our project, we used weather data from the KNMI, or the Royal Dutch Meteorological Institute. And their predictions are fairly accurate on average, but not always. I'll come back to that in a minute. Households predicting their consumption is way more difficult. because there's a very large variety in terms of production and consumption profiles. Clustering is really difficult because of that variety, but also making a model for each single household is not really feasible because you would need a lot of data before you can actually start modeling the consumption profile. And another big issue is if you have a small error in your prediction, if you're off by 1 hour, it can have very large consequences because if you suddenly sell your energy an hour too early or too late, the prices might have changed significantly. And not all weather forecasting data is perfect. So, well, different houses, different profiles. But here's an example of where a weather prediction is far from accurate. So the blue line you see is the prediction in the morning. And the purple line is what actually happened during that day. So some days they are really accurate. It's almost a complete match. But some days, maybe here the weather model thought, oh, there's going to be a cloud bank or something along those lines. And turns out there wasn't. So you would have missed out on trading because you might have thought, oh, I'm not going to produce as much during that hour. So that's also one of the issues here. I want to dive a little bit into the big batteries near solar parks. This is a really complex market, so I'm not going to go too far into detail. We can talk more about it during a break if you're really interested. But the bottom line is, in the physical setup, we had a large solar park with a 1 megawatt battery, industrial battery, that was really fast at supplying energy to the grid, but it was very slow at charging from the grid. So realistically, on this imbalance market, because going back a couple of slides, we had the two markets, the one that was slow the day ahead and one that was fast on almost a 1 minute level. Since you need to be able to supply energy quickly, you could only use it to, in this case, supply energy rather than also get energy from the grid. So the idea was to charge from excess solar, because you're connected to a solar park, a discharge to the grid on this fast energy market. In order to actually try to figure out, okay, how can you even do that? We set up an entire digital infrastructure where we took weather data, this is our partner that dealt with supplying the data from the solar park. Tenet is, of course, the grid operator to make sure that we get all the market prices that are relevant at that point. And ENSO similarly. And we all put it in our database. And what we ended up doing was we created a gym. And not the standard kind of gym, but the gym that was initially developed by OpenAI, that's now famous for very different things. They actually stopped maintaining Gym, and now another organization is maintaining Gym. And Gym is basically a playground / let's say standardized testing and development facility for reinforcement learning. And why did we go for reinforcement learning? Because it's really difficult to, let's say, create a label for what the correct action at a certain point in time would be, because it's a very complex system, and acting on the system also changes the environment. So reinforcement learning was the right fit for us there. So we dived into that, and we had 3 different, let's say, types of agents. One was very, very simple, baseline agent. It always bid the same amount, and that same amount was determined based on historical data. So it would basically do a brute force search of, okay, how much should I bid? And then the optimal choice for that would be used in the future. We also had an algorithmic approach that took into account the battery state of charge, early bids placed, where you are in the week, whether it's a weekday or a weekend day, and of course the market data. And reinforcement learning, where the agent placed bids based on battery, weather, market conditions, and it was obviously punished for bad behavior and rewarded for good behavior. And it turned out that, just a small visualization of here the orange line is the battery state of charge, We have income on different markets. You will see that this EPEX, that's the day-ahead market. Those prices are all negative because that is the income that you lose by not supplying your energy to the grid, but instead putting it into your battery. And later on, you use that energy on the AFRR market, which is the quick market, to turn a profit, ideally. Well, after lots and lots of training on 2022, turned out that the baseline earned roughly 10,000 euros over the course of a year. The algorithmic approach was a little bit better with 20,000, and reinforcement learning was even just a little bit better than that with 21,000, but to be honest, a marginal difference there, right? Only 1,000 euros over a year. And the funny thing of this reinforcement learning approach is relatively how close it is to an algorithmic approach that is, let's say, way easier to explain. So just to summarize, again, on the home batteries, so we have the arbitrage with the dynamic contract only. At this point, it's not profitable yet, right? You need like 15 years to earn back your battery. By that time, maybe pricings have changed as well, so it's really tricky to earn back on your investment. You might hear a lot of these different companies that say, okay, you can earn back your battery in 5 years. And the thing is, they don't do just arbitrage. They usually do a combination of arbitrage and imbalance markets. So that's where that claim is coming from. Self-usage is, let's say, from the nets or from the grid's perspective, the most ideal one, because you don't bother the grid with extra traffic, because you're charging and discharging from the grid and to the grid, but also not really profitable at this point. And imbalance is only really possible if you're part of an aggregator as a small consumer, because you need the big capacity, you need the 1 megawatt. But it's also an issue if all of those things start doing the same activity at the same time, because you're being activated by your aggregator, you can increase in that congestion as well. And at this moment, the yields are high, but the future is unclear because of the removal of the salderingsregeling or the net metering arrangement. That was it. Are there any questions?
Yeah, I have a question.
Yes.
As an owner of a battery.
Yes.
Sorry.
Excellent.
Yeah, I was wondering. You were saying that actually the prediction is that if you're working on this imbalance market,
Yeah.
and which I am, and all of a sudden everybody starts to pump down electricity from the net, you could have the congestion problem.
Correct.
But I think the reason that we do this is actually that the prices are so high, so you get paid for it, is net congestion.
Yes and no, because congestion, you can have congestion on a local level, so on the level of a part of a town or something, and some of the other imbalance that you get paid for if you deal with imbalance on the AFRR market, they are, let's say, on a national level. So you have these different, basically, markets competing against each other, and by solving one problem, you start it elsewhere. Good question, thank you.
I think it's true that if you would give TenneT the ability to charge and discharge batteries, that they could actually solve the congestion instead of that the batteries are causing congestion. Yeah, what do you think about that, and why isn't that there yet?
So the easy answer, as far as I understood, is that it's not there yet because on the one hand, you don't have the infrastructure for it yet, because they need some kind of control mechanism to shut off your battery or to restart it, etc. And also, if you would suddenly introduce that, people who've already bought their batteries are going to be like, okay, why is somebody else suddenly controlling my battery, right? And how do you divide the, let's say, profits? To which extent is saved costs a profit? I mean, technically it's a profit, but you can't really hand out the money. So it's almost more of a policy and a business challenge than a technical in that sense, I think. The question is, to what extent do you want this this party outside of your own control controlling your assets, or should we? As long as you get paid for it.
No, I mean, mine is actually controlled by another much smaller party,
Mm-hmm.
which I wouldn't even. Well, if it. Sorry. Mine is controlled by a company called Blick.
Mm-hmm.
Interesting people. And I would actually trust much more a big party like Tenet.
Mm-hmm.
I think it's actually something which has to do with bureaucracy within Tenet.
Mm-hmm.
That's just taking bloody too much time to solve problems. And because these things are just there, they could actually do that. And to finance the whole thing, give people these batteries at home and have them like orchestrate those batteries.
Mm-hmm.
I mean, small companies are doing it, but small companies are just more flexible and easier adapting than this huge Tenet. That's,
Mm-hmm.
I think there's a problem. So
Yeah, yeah.
they should actually get in gear and do something.
Mm-hmm. And maybe as a kind of a frame challenge, and also to some extent a frame challenge to my own story, because lots of people are getting electric vehicles, right? And electric vehicles already have a battery built in that you could use, but right now it's not really common to use your battery to reduce, for example, imbalance on the grid yet. And I think it would be way more preferable to use that flexibility that people already have to some extent, rather than just putting batteries into people's homes. If you do need the batteries, and you're saying, okay, it might be better for a bigger party like Tenet to deal with controlling those batteries, then why even go through the extra hoop of placing them in people's homes, and instead not just put industrial batteries in or near places where there's lots of congestion. You probably need both, yeah. And of course, also that's a nice thing of saying, okay, we're going to use home batteries for this. If you encourage consumers to start purchasing these home batteries, it's also a way for the grid operator to more, in that sense, efficiently manage the grid. Because if people are spending their own money on purchasing things that reduce the imbalance on the grid, that's only to their benefit, right? To the grid operator's benefit. Yeah. And of course, for example, all these figures that I just mentioned are with the current prices, right? Battery prices are projected to go down. So at this point, I would say there's not a business case for just pure energy arbitrage. But in the future, if batteries get cheaper, probably.
Yeah. Hi. Completely unrelated question, maybe. But so when everybody starts buying these home batteries, what about safety and fire hazard? Because have you already seen a burning Tesla? If you don't want to have this stuff in your house, right? Because if you can put a burning Tesla in a container, but it's quite difficult to pick up your house and put that one in a container. So what? And it's about statistics, right? Because what is the chances of a home battery burning? Very, very low. But if everybody in the street has a home battery, then I know I'm from IT, so I know hard disks fails.
Yeah.
Also, home batteries will fail and will burn. So what is your idea about this?
That's a good question. It's something I didn't really dive into because it's kind of out of scope of, let's say, the control mechanisms and smart control. But if you say, just as a thought experiment, let's imagine that everybody has or needs to have a home battery, then I assume that there will also be more, let's say, stringent conditions from, for example, insurers to be able to insure your own home if everybody has a home battery. Because in the end, if your house burns down because of a home battery, your insurance is going to be the one hopefully paying for it, because it's not at the fault of yours. So they would probably, in some way or shape or form, try to enforce maybe regular inspections or certified technicians checking it or something along those lines. Would be my educated guess, or maybe my uneducated guess is better phrasing.
But that would then drive up the prices of a home battery, right? In one way or the other way.
In one way or the other, yes, definitely.
So that would then also be included in in your pricing mechanism, so that will because the batteries will be more expensive instead of cheaper.
Yeah, and then it might become a question of, okay, so maybe if at some tipping point these home batteries are no longer profitable, are there some other way we could incorporate these batteries into the Dutch electricity grid, rather than putting them inside of homes, but maybe in other buildings?
Outside in a field, maybe.
I think that's more prone to degradation than just inside.
Okay, thank you.
All right, looking at the time, it's already half, so we are out of time. So I want to thank you all.